Most men believe they understand what they see every day. You wake each morning as sunlight enters your chamber.
You light a candle to read by evening. You see your reflection in still water. Light seems the most familiar thing in creation, yet it conceals the most profound mystery I've encountered in all my studies of natural philosophy. When I first placed a glass prism in a beam of sunlight 30 years ago, I expected nothing remarkable. Light was light, white, and pure, as God made it. What emerged instead challenged everything learned men believed about the nature of illumination itself. That simple experiment revealed that what we call white light contains within it all the colors of creation, perfectly ordered and mathematically precise. The implications reach far beyond mere curiosity. Understanding light's true nature unlocks secrets about vision, about the heavens, about why we perceive the world as we do. Before we continue, take a moment to notice where you're listening from, and if this story stays with you, you're welcome to return tomorrow for what comes next. I arrived at Trinity College, Cambridge in the summer of 1661, carrying little more than a few books and an insatiable curiosity about the workings of God's creation. The world then seemed ordered and comprehensible. Aristotle's philosophy dominated the curriculum, and learned men spoke with confidence about the four elements, the humors, and the celestial spheres. I absorbed these teachings dutifully, but something within me questioned whether the ancients had truly understood the mechanisms they described. My first encounter with serious optical work came through my attempts to construct a telescope. The instrument had been known for barely 50 years, yet already it promised to unlock the heavens. I ground my own lenses with meticulous care, following the methods described in text, but the results frustrated me. Every telescope I built suffered from the same defect. Colored fringes surrounded every object I observed. Stars appeared as tiny rainbows rather than points of light. The moon's craters were bordered with unwanted hues. The accepted explanation blamed imperfections in the glass. Learned opticians spoke of improving lens quality, of finding purer materials, of perfecting the grinding techniques. Yet I began to suspect something deeper was at work. Why did the colors always appear in the same order? Why did red consistently occupy the outer edge, blue the inner? Random imperfections should produce random effects, but these colors followed a strict pattern. My investigations might have proceeded slowly within Cambridge's walls, constrained by the demands of formal study. But in 1665, the plague arrived in England with terrible force. The university closed, sending students to their homes until the pestilence passed. For me, this meant returning to my family's manor at Woolsthorpe in Lincolnshire. Those 18 months of enforced isolation became the most productive period of my life. With no lectures to attend, no prescribed readings to complete, I was free to pursue my own investigations. The manor's rooms became my laboratory. I converted the upper chamber into an optical workshop, covering windows with shutters to control the light, arranging tables for my instruments, and preparing surfaces for precise measurements. During those quiet months, I polished mirror after mirror for my telescopes. The work required absolute patience. Each surface had to be ground to mathematical perfection, the curve following precise geometric principles. As I worked, I observed how light behaved when it struck different materials. Polished metal reflected cleanly. Rough surfaces scattered the rays in all directions. Glass both reflected and transmitted, bending the light as it passed through. This bending, or refraction, fascinated me most. When I placed a stick in water, it appeared broken at the surface. When I looked through a glass of wine, objects behind it shifted position. Every transparent substance seemed to alter light's path according to its own rules. Yet the explanations I found in Aristotle and other ancient sources felt inadequate. They spoke of light as a quality, a form of being, but they provided no mathematical description of its behavior. I began to suspect that light itself might be more complex than anyone imagined. The telescope's colored fringes suggested that white light was not the simple, pure substance we believed it to be. Perhaps those colors were not aberrations, but revelations, signs of light's hidden nature made visible through the glass. My first systematic experiments began with water. I filled glass vessels of different shapes and observed how light bent when passing through them. Spherical containers produced one effect, cylindrical another, flat-sided vessels created yet different patterns. Each shape revealed new aspects of light's behavior, but the underlying principle eluded me. I turned next to glass prisms, triangular pieces that opticians sometimes used in their work. When I held one up to candlelight, I noticed that the flame appeared displaced, shifted from its actual position. More intriguingly, the displaced image sometimes showed hints of color at its edges. These colors were faint but unmistakable, always appearing in the same sequence. The pattern intrigued me. If white light were truly pure and indivisible, as natural philosophers taught, why did it consistently separate into these particular colors when passing through certain materials? Why did red always appear on one side, blue on the other? The regularity suggested an underlying order, a mathematical relationship waiting to be discovered. I began to formulate a hypothesis that would have shocked my former teachers. Perhaps white light was not pure at all. Perhaps it contained within itself all these colors, normally invisible but capable of being separated under the right conditions. The idea seemed radical, even heretical, challenging centuries of accepted wisdom. Yet the evidence from my crude experiments pointed in this direction. As the plague months continued, I refined my techniques. I learned to control the light more precisely, to position my prisms at exact angles, to measure the resulting effects with mathematical precision. Each experiment built upon the last, each observation added another piece to the emerging puzzle. By the time Cambridge reopened in 1667, I had filled several notebooks with observations and calculations. The colored fringes in my telescopes no longer seemed like mere imperfections to be corrected. They were clues to something fundamental about the nature of light itself, symptoms of a hidden complexity that no natural philosopher had yet recognized. I returned to my formal studies with a secret knowledge. While my fellow students continued to accept the ancient teachings about light and vision, I carried within me the seeds of a revolutionary understanding. The familiar world of white sunlight and clear glass concealed mechanisms of breathtaking elegance and mathematical beauty. But I knew that my preliminary observations, however compelling to me personally, would convince no one else. The learned world demanded proof, not speculation. To overturn centuries of teaching, I would need experiments so clear, so undeniable, that even the most conservative natural philosophers would be forced to accept their implications. The time had come for more decisive action. I began to plan the experiment that would reveal light's true nature to the world, an investigation so simple in concept yet so profound in its implications that it would transform our understanding of vision, color, and the fundamental workings of creation itself. The experiment that would change everything required the simplest of preparations. I chose the upper chamber at Woolsthorpe, a room with a single window facing south to catch the strongest sunlight. With wooden boards and black cloth, I sealed every opening save for a small hole, no wider than my thumb, which I cut through the shutter. When complete, the chamber lay in perfect darkness except for that single beam of sunlight that entered like a golden sword through the aperture. I'd performed variations of this setup before, but never with such methodical precision. This time I would control every variable, measure every angle, record every observation with mathematical accuracy. The reputation of natural philosophy itself seemed to rest on such careful procedure, for too many conclusions had been drawn from hasty observations and wishful thinking. My prism waited on the table, a triangular piece of glass I had acquired from a London optician. It was perhaps 3 inches long, perfectly clear, with faces ground smooth and true. In ordinary light, it appeared unremarkable, just another piece of worked glass such as any craftsman might produce. Yet I suspected this humble object held the key to understanding light's deepest secrets. I positioned myself in the darkened room and allowed my eyes to adjust to the gloom. The single beam of sunlight painted a bright circle on the opposite wall, pure white and sharply defined. This was light as God made it, as every natural philosopher understood it to be, simple, indivisible, perfect in its unity. With steady hands, I placed the prism in the beam's path. What happened next defied every expectation I had formed during my years of study. The white circle of light vanished, replaced by an elongated band of colors stretching across the wall like a fragment of rainbow brought indoors. Red occupied one end of the spectrum, shading gradually through orange and yellow to green, then blue, and finally deep violet at the opposite extreme. The transformation was so sudden, so complete, that I found myself staring in silence for several minutes. This was not the faint coloration I had observed at the edges of telescope images. This was vivid, unmistakable, beautiful in its clarity. Every color of creation lay spread before me, emerged from what had appeared to be colorless light. My first thought was that the prism had somehow created these colors, that the glass itself was adding something to the light that passed through it. This explanation accorded with the teachings I had absorbed at Cambridge, where learned men spoke of colors as modifications of pure light, corruptions introduced by imperfect media. Perhaps the prism's irregularities were responsible for this spectacular display. And as I examined the phenomenon more carefully, doubts arose. The colors appeared in the same order every time I repeated the experiment. Red always occupied the same position relative to the incoming light.
Violet always appeared at the opposite end.
The sequence never varied, never randomized, never showed the irregularity one would expect from mere imperfections in the glass. More puzzling still, each color within the spectrum appeared pure and saturated, not muddy or mixed as one might expect if the prism were corrupting the light. The red was as vivid as blood, the blue as deep as a summer sky. These were not degraded versions of white light, but distinct, perfect colors in their own right. I moved closer to examine individual parts of the spectrum. When I blocked the red portion with my hand, only the remaining colors appeared on the wall. When I blocked the blue, the red, and other hues continued unaffected. Each color behaved independently, following its own path through the glass, bending by its own particular angle. This observation struck me with the force of revelation. If the prism were merely modifying or corrupting pure white light, then blocking any portion should affect the whole. Instead, I was seeing evidence that white light contained these colors as distinct components, each following its own mathematical rules. I spent the remainder of that day repeating the experiment with different prisms, different angles, different positions. Every trial produced the same result. White sunlight, when properly analyzed, revealed itself to be composed of all the colors of the visible world, arranged in perfect mathematical order. The implications overwhelmed me. If white light contained all colors within itself, then color was not something added to light by external objects. Color was fundamental, built into the very nature of illumination itself. The red of a rose, the blue of the sky, the green of leaves in spring, all these were not qualities that objects possessed, but selections they made from the full spectrum of light that fell upon them. I began to understand why my telescopes had shown colored fringes around every object. Different colors within white light were being bent by different amounts as they passed through the lenses. What I had taken for imperfections were actually revelations of light's true complexity, visible symptoms of the invisible spectrum contained within every beam of sunlight. As evening approached and the sunbeam faded, I remained in the darkened chamber, contemplating what I had witnessed. In the span of a single afternoon, the accepted understanding of light and color had crumbled before my eyes. Aristotle's teachings, the wisdom of centuries, the confident assertions of contemporary natural philosophers all had been revealed as inadequate, based on incomplete observation of light's true nature. I knew that my own eyes might deceive me, that personal conviction meant nothing in natural philosophy without rigorous proof. The Royal Society in London was filled with learned men who would demand evidence beyond mere spectacle. They would want measurements, repetitions, mathematical demonstrations. They would challenge every assumption, question every conclusion. I welcomed their skepticism, for it would force me to perfect my understanding. The experiment I had just performed was only the beginning, the first step in a longer investigation that would map light's behavior with unprecedented precision. But already I felt certain of the fundamental discovery: white light was not simple but composite, not pure but complex, containing within itself all the colors of creation in perfect mathematical harmony. The prism had not created colors from white light. It had revealed colors that were already there, waiting to be discovered by anyone bold enough to look carefully at what seemed most familiar and obvious in the natural world. The weight of what I had discovered settled upon me gradually over the following days. I had not merely observed an interesting optical effect or discovered a curious property of glass prisms. I'd stumbled upon evidence that contradicted the fundamental teachings about light and color that had governed natural philosophy for nearly 2,000 years. Aristotle himself had written extensively on the nature of colors in his work on meteorology. According to the great philosopher, colors arose from the mixture of light and darkness, brightness and shadow. White represented pure light, black pure darkness, and all other colors were various combinations of these two extremes. This explanation had satisfied generations of scholars because it accorded with common observation. Mix white and black paint, and you indeed produce gray. Add more black, and the gray darkens toward true black. The theory extended beyond simple mixing. Aristotle taught that transparent media could modify light by introducing varying degrees of darkness, thus producing different colors. A piece of colored glass appeared colored because it added darkness to the pure light passing through it. The redness of wine, the greenness of emerald, the blueness of sapphire all resulted from each substance contributing its particular shade of darkness to contaminate the white light. This understanding had been refined by medieval scholars and embraced by the natural philosophers of my own time. Robert Hooke, one of England's most respected investigators of nature, had recently published theories that built upon Aristotelian foundations. According to Hooke, colors resulted from the modification of light pulses as they encountered different media. The modifications were complex, involving vibrations and disturbances, but the fundamental principle remained Aristotelian. Pure white light was being changed into something else. My prism experiment challenged this entire edifice of thought. If white light truly contained all colors within itself, as my observation suggested, then colors were not modifications of light but constituents of it. They were not corruptions introduced by external media, but inherent components waiting to be separated and revealed. The implications troubled me deeply, not because I doubted my observations, but because I understood what it meant to challenge such ancient and widely accepted doctrine. Natural philosophy in the 17th century still revered classical learning. Aristotle's works were studied not merely as historical curiosities, but as living sources of truth about the natural world. To suggest that the great philosopher had been fundamentally mistaken about something as basic as the nature of color bordered on intellectual presumption of the highest order. Yet the evidence of my eyes could not be denied. Night after night, I returned to the darkened chamber and repeated the experiment,
White sunlight consistently separated into the same spectrum of colors.
always in the same order, always with the same mathematical precision. If Aristotle were correct, if colors truly resulted from mixtures of light and darkness, then I should be able to create any color by combining white light with appropriate amounts of shadow. But every attempt to do so failed. Adding darkness to white light produced only dimmer white light, never the vivid reds and blues I observed in the spectrum. More telling still, I discovered that I could isolate individual colors from the spectrum and pass them through additional prisms. Pure red light separated from white light and sent through a second prism emerged still red, unchanged by its passage through the glass. If red resulted from white light mixed with a particular quantity of darkness, then the second prism should modify it further, adding more darkness or changing the mixture in some way. Instead, the red remained perfectly red, revealing itself to be fundamental rather than composite. I performed this test with every color in the spectrum. Blue light passed through additional prisms remained blue. Green remained green. Yellow remained yellow. Each color proved irreducible, incapable of being broken down into simpler components or modified by the processes that Aristotelian theory claimed created them in the first place. The evidence compelled me toward a revolutionary conclusion. Colors were not modifications of white light, but the elements from which white light was composed. Just as white light could be separated into individual colors by a prism, those same colors could presumably be recombined to recreate white light. The spectrum was not a degradation of pure light, but an analysis of it, revealing its hidden structure. This understanding cast new light on countless everyday observations. When I looked at a red rose in my garden, I was not seeing white light that the flower had somehow modified by adding darkness. I was seeing the red component of white sunlight reflected back to my eyes while the other colors were absorbed into the petals. The rose was not creating redness, but selecting it from the full spectrum of illumination that fell upon it. Similarly, the blue of the sky resulted not from the air adding blueness to sunlight, but from some mechanism that scattered blue light more readily than other colors, sending it in all directions while allowing red and yellow to pass through relatively undisturbed. Every colored object in creation was performing a kind of analysis of white light, choosing which components to reflect and which to absorb. The elegance of this new understanding fascinated me, but its implications also generated considerable anxiety. I was not merely proposing a new theory about light and color. I was suggesting that some of the greatest minds in human history had fundamentally misunderstood one of the most basic phenomena in nature. Aristotle, Aquinas, Bacon, Descartes all had built their optical theories on the assumption that white light was simple and colors were complex. My experiments suggested the opposite. Colors were simple, white light was complex. I knew that such claims would provoke fierce resistance from the learned community. Natural philosophers had invested their reputations in theories based on Aristotelian principles. University curricula, scholarly treatises, and public lectures all assumed that light and color behaved as the ancients had described. To overturn such established doctrine, I would need evidence so overwhelming, demonstrations so clear, that even the most conservative scholars would be forced to abandon their cherished beliefs. The task ahead seemed daunting, but the truth of my observations compelled me forward. I began to design additional experiments that would prove beyond doubt that white light was composite rather than simple, that colors were fundamental rather than derived. The ancient wisdom would have to yield to modern evidence, no matter how painful that surrender might prove to be.
The definitive proof I sought required reversing the process I had already demonstrated.
If white light truly contained all colors within itself, then it should be possible to take those separated colors and recombine them back into white light. This experiment would provide the crucial evidence that colors were not corruptions of pure light, but its fundamental constituents. I spent several days preparing for this investigation, knowing that it would demand even greater precision than my initial observations. The darkened chamber needed modifications. I required not one but two prisms, positioned with mathematical exactness to first separate the colors and then reunite them. Any misalignment would blur the results and provide ammunition for critics who might claim my conclusions were based on imperfect observations. My first challenge was obtaining a second prism of suitable quality. The London optician, who had provided my original piece, was able to supply another, ground to similar specifications. I examined both prisms carefully under strong light, checking for bubbles, scratches, or irregularities that might affect their performance. The glass had to be perfect, for this experiment would settle the question of light's nature once and for all. I arranged the apparatus with meticulous care. The first prism occupied its familiar position in the beam of sunlight, casting its spectrum of colors across the chamber. But now, instead of allowing those colors to strike the wall, I intercepted them with the second prism, positioned at precisely the angle needed to bend the separated rays back toward convergence. The theory was elegant in its simplicity. If white light was indeed composite made up of individual colored rays, then the second prism should bend each color by exactly the amount needed to reunite them. Red light, having been bent least by the first prism, would be bent most by the second. Blue light, bent most by the first, would be bent least by the second. The mathematical relationships I had observed in the original separation should work in reverse, bringing all colors back together into a single beam. I made my final adjustments and stepped back to observe the result. On the wall where the recombined beam struck, I saw white light. Not the muddy gray I might have expected if colors were mere corruptions of pure light. Not a dim or tinted illumination that suggested incomplete mixing. Perfect white light, as pure and brilliant as the original sunbeam that entered through my small aperture. I stood transfixed by this demonstration for several long minutes. Here was proof that could convince the most skeptical natural philosopher. White light separated into colors by one prism, then recombined into white light by another. The process was perfectly reversible, revealing that no information was lost in the separation, no essence was destroyed or modified. The colors had been present in the original white light all along, waiting to be revealed and then reunited. To ensure the validity of my observation, I repeated the experiment with different arrangements. I varied the distance between prisms, changed the angle slightly, and adjusted the position of the recombined beam. In every case, when the geometry was correct, perfect white light emerged from the second prism. When I deliberately misaligned the apparatus, the result showed obvious coloration, proving that the whiteness was not accidental, but the precise consequence of proper recombination. I then performed what I considered the most convincing demonstration of all. Using a narrow board, I blocked individual colors in the spectrum between the two prisms. When I prevented red light from reaching the second prism, the recombined beam appeared cyan, lacking only the red component. When I blocked blue, the result was yellow-orange. When I blocked yellow, the remainder combined to form a purplish hue. Each color I removed from the spectrum left its unmistakable mark on the final result, proving that every component was essential to creating perfect white light. This experiment demolished any remaining doubt about light's composite nature. The spectrum was not a degradation of white light, but an analysis of it. The second prism was not corrupting the separated colors, but revealing their fundamental unity. I had demonstrated that white light was complex while individual colors were simple, overturning 2 millennia of accepted wisdom. The mathematical precision of the process particularly impressed me. Each color bent by exactly the amount required for proper recombination, following geometric laws as strict as those governing planetary motion. There was nothing random or approximate about the phenomenon. Light obeyed mathematical rules with the same precision I had discovered in my studies of mechanics and gravitation. I began to understand why my telescope designs had suffered from chromatic aberration. Different colors within white light were being bent by different amounts as they passed through the lenses. Since telescope makers had assumed light was uniform, they had designed their instruments based on average behavior rather than accounting for the spectrum of colors actually present in every beam. The colored fringes around celestial objects were not imperfections to be corrected, but inevitable consequences of light's true nature. This realization suggested practical applications for my discoveries. If I could design optical instruments that accounted for light's composite nature, I might create telescopes superior to any previously constructed. Perhaps lenses could be combined in ways that compensated for the different behavior of different colors. Or perhaps reflecting telescopes using mirrors instead of lenses could avoid chromatic problems entirely. But before pursuing such applications, I knew I needed to share my findings with the community of natural philosophers. The Royal Society of London had been established precisely to investigate such questions about the natural world. Their members included the most learned men in England, individuals capable of understanding the significance of my discoveries and helping to establish them as accepted knowledge. I began drafting a letter to the Society's secretary describing my experiments and their implications. The task proved more difficult than I had anticipated, not because the observations were complex, but because their consequences were so far-reaching. I was not simply reporting a new phenomenon, but proposing a fundamental revision of optical theory. As I wrote, I tried to anticipate the objections my claims would provoke. Conservative philosophers would resist abandoning Aristotelian teachings. Practical opticians might question whether my laboratory demonstrations applied to real-world situations. Religious thinkers might worry about the implications for understanding divine creation. I would need to address each concern with patience and precision, providing evidence so compelling that resistance would gradually give way to acceptance. The recombination experiment had given me that evidence. No one could witness the perfect restoration of white light from separated colors and continue to believe that those colors were mere corruptions or modifications. The demonstration proved conclusively that light's true nature was the opposite of everything previously taught, not simple but composite, not pure but wonderfully complex, containing within itself all the colors of creation in perfect mathematical harmony. In February of 1672, I finally dispatched my letter to Henry Oldenburg, Secretary of the Royal Society. The document contained a careful description of my prism experiments and their implications for understanding light and color. I had labored over every sentence, knowing that these pages would either establish my reputation as a natural philosopher or mark me as a presumptuous young man who dared challenge the wisdom of ages. The Society's response exceeded my expectations. At their meeting of February 8th, the members received my communication with considerable interest. Several expressed eagerness to repeat my experiments, while others praised the mathematical precision of my observations. For a brief moment, I allowed myself to hope that the truth of my discoveries would speak so clearly that acceptance would follow without significant controversy. I was mistaken. Within weeks, letters began arriving that challenged every aspect of my work. The most pointed criticism came from Robert Hooke, the Society's curator of experiments and one of England's most respected investigators of natural phenomena. Hooke had made significant contributions to optics, microscopy, and mechanical philosophy. His book Micrographia had revealed the hidden world visible through magnifying lenses, earning him fame throughout learned Europe. When such a man questioned my conclusions, the entire natural philosophy community took notice. Hooke's objections struck at the heart of my theory. He argued that my experiments, while ingenious, proved nothing about light's fundamental nature. The colors I observed emerging from prisms might result from the glass modifying white light, rather than revealing components already present within it.
Different parts of the prism could introduce different modifications,
creating an artificial spectrum that had no relation to light's true composition. This critique stung because it revealed how difficult it was to prove that colors were inherent in light rather than created by the prism. When I separated white light into a spectrum, skeptics could always claim the prism was adding something rather than revealing something. When I recombined the colors back into white light, they could argue that the second prism was simply undoing the modifications introduced by the first. Hooke went further, suggesting that his own wave theory of light provided a superior explanation of my observations. According to his understanding, light consisted of vibrations transmitted through a subtle medium that filled all space. Different colors corresponded to different types of vibrations, and prisms could modify these vibrations in ways that produced the effects I had observed. This theory preserved the fundamental simplicity of white light while accounting for the phenomena I claimed to have discovered. Other critics joined the attack from different angles. Some questioned whether my darkened chamber experiments accurately represented how light behaved in ordinary circumstances. Perhaps the controlled conditions I had created produced artificial effects that bore no relation to natural illumination. Others suggested that my conclusions applied only to the particular prisms I had used, made from specific types of glass by particular craftsmen. The most troubling objection concerned the practical implications of my theory. If white light truly contained all colors, critics asked, why did objects appear consistently colored? A red rose looked red in morning sunlight, at midday, and in evening illumination. If sunlight's composition varied with atmospheric conditions or the angle of the sun, shouldn't the rose's color change accordingly? The constancy of color in everyday experience seemed to contradict my claims about light's variable nature. I found myself engaged in a lengthy correspondence defending my experiments against each objection while trying to extend my observations to address new questions. The process proved exhausting and sometimes discouraging. I'd expected natural philosophers to embrace discoveries that revealed new truths about creation. Instead, I encountered skepticism that sometimes bordered on hostility.
Yet the challenges forced me to refine my understanding and develop more convincing demonstrations.
To address Hooke's claim that prisms modified rather than revealed light's properties, I designed experiments showing that individual colors, once separated, could not be further analyzed by additional prisms. Pure red light passed through any number of prisms remained pure red, proving that it was fundamental rather than composite. I also demonstrated that different transparent materials, water, various types of glass, even crystalline substances, all separated white light into the same sequence of colors. If prisms were creating colors through their own modifications, different materials should produce different effects. The universality of the spectrum argued strongly that colors were inherent properties of light itself. To counter arguments about artificial laboratory conditions, I extended my observations to natural phenomena. Rainbows, I realized, were simply prism experiments performed by nature herself. Countless water droplets in the air acted as tiny prisms, separating sunlight into its component colors and creating the familiar arc across the sky. The rainbow's color sequence matched exactly what I observed in my chamber, providing powerful evidence that my controlled experiments revealed universal truths about light's behavior. The correspondence with Hooke grew particularly heated when he suggested that I had merely rediscovered phenomena he had already explained through wave theory. I responded by pointing out that observation was one thing, explanation another. Even if Hooke had noticed colored effects in optical experiments, he had not recognized their true significance or provided an accurate account of their cause. His wave theory, while mathematically sophisticated, preserved the fundamental error of treating white light as simple rather than composite. As months passed, I began to understand that convincing the learned world would require more than logical arguments and careful experiments. Natural philosophy in the 17th century was as much about authority and reputation as about evidence and reasoning. Hooke commanded respect based on decades of productive research. I was a young man, barely known outside Cambridge, challenging established doctrine with claims that seemed to overturn basic assumptions about the natural world. The controversy taught me valuable lessons about the social aspects of scientific discovery. Truth alone was insufficient. Truth had to be communicated persuasively, defended against criticism, and promoted through networks of scholarly correspondence. The Royal Society provided a forum for such activities, but success required patience, persistence, and political skill as much as experimental ability. Despite the frustrations, I remained confident in my observations and their implications. Every repetition of the prism experiments confirmed my original conclusions. Every extension of the work revealed new aspects of light's composite nature. The mathematical relationships I had discovered proved robust under varied conditions and different experimental arrangements. I began to see the criticism as ultimately beneficial, forcing me to strengthen weak arguments and address overlooked questions. Hooke's challenges, while sometimes unfair, compelled me to develop more sophisticated explanations and more convincing demonstrations. The controversy generated interest in optical questions throughout Europe, encouraging other natural philosophers to repeat my experiments and extend my observations. By the end of 1672, I had established my position within the community of natural philosophers, not as an unquestioned authority, but as a serious investigator whose work demanded careful consideration. The battle over light's nature would continue for years, but the foundation had been laid for eventual acceptance of the composite theory. Truth, I had learned, advanced not through sudden revelation, but through gradual accumulation of evidence, persistent argument, and the slow erosion of established error. The debates with Hooke and other critics revealed gaps in my understanding that mere qualitative observations could not fill. While I had demonstrated that white light was composite and that colors could be separated and recombined, I had not yet established the precise mathematical relationships that governed these phenomena. Natural philosophy demanded more than descriptive accounts. It required the kind of quantitative analysis that had proven so successful in mechanics and astronomy. I returned to my darkened chamber with a new purpose. This time, I would measure everything: the angles at which different colors emerged from the prism, the exact positions they occupied in the spectrum, the mathematical relationships between incident rays and refracted rays. Only through such precise measurement could I hope to establish laws as rigorous as those governing planetary motion. My first task was to determine exactly how much each color bent when passing through the prism. I constructed a careful measuring apparatus, using threads to mark the paths of incoming and outgoing rays, protractors to measure angles, and rulers to record distances. The work required extraordinary patience, for each measurement had to be repeated multiple times to ensure accuracy. What I discovered astonished me. Each color had its own specific index of refraction, its own mathematical relationship between the angle of incidence and the angle of refraction. Red light, which appeared at one end of the spectrum, bent least when entering the prism. Orange bent slightly more, yellow more still, then green, blue, and finally violet, which showed the greatest deviation from its original path. The progression was not random, but followed a precise mathematical sequence. When I plotted the refraction angles against the position of each color in the spectrum, I obtained a smooth curve that could be described by a mathematical formula. This was not mere correlation, but causation. The degree to which each color bent determined its position in the spectrum, and that degree followed immutable mathematical laws. I extended these measurements to different types of glass and discovered that while the absolute values changed, the relative relationships remained constant. Red always bent least, violet always bent most, and the intermediate colors always occupied the same sequence. This universality suggested that I was observing fundamental properties of light itself, not accidents of particular materials. The mathematical precision of these relationships provided powerful ammunition against critics who claimed that prisms arbitrarily modified white light. If the glass were simply adding modifications or corruptions, why would those modifications follow such exact mathematical rules? Why would every type of transparent material impose the same sequence of changes? The regularity pointed unmistakably toward inherent properties of light rather than external impositions by matter. I began to understand why the ancients had been deceived about light's nature. Without precise measurement, the differences between colors appeared qualitative rather than quantitative. Red seemed fundamentally different from blue, in the same way that hot differed from cold or rough from smooth. But mathematical analysis revealed that colors differed only in degree, in the exact amount by which they bent when passing through transparent media. Insight suggested a deeper unity underlying the apparent diversity of colors. Perhaps all light, regardless of color, obeyed the same fundamental laws, with the differences we observed resulting from quantitative variations in some underlying property. I began to suspect that color was related to what we might call the refrangibility of light, its tendency to bend when passing from one medium to another. The mathematical relationships I discovered had immediate practical implications for optical instrument design. The chromatic aberrations that plague telescopes resulted from different colors focusing at slightly different distances behind a lens. By understanding exactly how much each color bent, I could calculate where each would come to focus and potentially design compound lenses that compensated for these differences. But achieving such compensation proved more difficult than I had anticipated. The mathematical relationships that governed refraction were not arbitrary, they reflected deep properties of light and matter that could not be easily altered. Simple combinations of lenses made from ordinary glass could reduce chromatic aberration, but never eliminate it entirely. The fundamental physics imposed limits that no amount of clever design could overcome. This realization led me to explore reflecting telescopes as an alternative to refracting instruments. Mirrors reflected all colors equally, avoiding the chromatic problems inherent in lenses. I spent considerable time grinding and polishing metal mirrors, learning the precise techniques needed to achieve the mathematical perfection that effective reflection required. My first reflecting telescope, though small, produced images noticeably superior to those from refracting instruments of similar size. Stars appeared as sharp points of light rather than tiny rainbows, and planetary details previously obscured by colored fringes became clearly visible. The mathematical understanding derived from my prism experiments had led directly to practical improvements in astronomical observation. As I continued measuring the behavior of different colors, I made another significant discovery. The spectrum was not merely a sequence of discrete colors, but a continuous range of refrangibilities. Between what we called red and orange lay intermediate hues, each with its own specific mathematical properties. The boundaries between named colors were human conventions rather than natural divisions. This observation suggested that light might contain infinitely many distinct components, each characterized by its own precise refrangibility. The familiar colors red, orange, yellow, green, blue, violet were simply samples from this continuous spectrum, the portions to which our eyes were most sensitive. The mathematical analysis revealed a richness in light's composition that exceeded anything suggested by casual observation. I began to understand why certain combinations of colors produced white light while others did not. The mathematical relationships governing refraction also determined how colors combined. White light resulted from the proper mixture of all refrangibilities in specific proportions. Any deviation from these proportions produced a tinted result, with the exact hue determined by which parts of the spectrum were overrepresented or underrepresented. These discoveries provided the foundation for what I began to call the theory of colors, a mathematical framework that explained all the phenomena I had observed and predicted new effects that could be tested experimentally. Unlike previous theories based on philosophical speculation, this framework rested on precise measurements and quantitative relationships that could be verified by any careful investigator. The mathematical precision of light's behavior convinced me that I was studying one of nature's fundamental mechanisms, a process as basic as gravitation or motion. The same geometric principles that govern the paths of planets around the sun also determined how colors behaved when passing through prisms or reflecting from mirrors. The unity of natural law extended even to phenomena as apparently different as celestial mechanics and the spectrum of sunlight. As I compiled my measurements and calculations into a systematic account, I realized that mathematics had transformed my understanding of light from mere description to prediction. I could now calculate exactly how any optical system would behave, predict the colors that would emerge from any combination of prisms and mirrors, and design instruments that achieved specific optical effects. The mathematical analysis had elevated optics from a craft based on trial and error to a science based on quantitative law. For 30 years after my initial discoveries with prisms, I hesitated to publish a complete account of my optical investigations. The controversies that had followed my first paper to the Royal Society had taught me how fiercely the learned world could resist new ideas, especially those that challenged fundamental assumptions about nature. I had no desire to spend my remaining years defending theories against critics who seemed more interested in preserving established doctrine than in discovering truth. Yet the evidence continued to accumulate. Every experiment confirmed my understanding of light's composite nature. Every mathematical calculation strengthened the quantitative framework I had developed. Other natural philosophers, repeating my demonstrations across Europe, gradually began to accept that white light was indeed complex rather than simple. The time seemed right to present a comprehensive account that would settle the question definitively. I began work on what would become optics in the early 1690s, drawing upon decades of observations, measurements, and theoretical development. The task proved more challenging than I had anticipated, not because the science was difficult, but because I needed to present revolutionary ideas in ways that would convince rather than antagonize readers. I had learned from my earlier experiences that even correct theories could be rejected if they were communicated poorly. The book's structure reflected my conviction that natural philosophy should build systematically from observation through measurement to mathematical law. I began with simple experiments that any reader could repeat, gradually building toward more complex demonstrations and theoretical conclusions. Each proposition rested on experimental evidence, each conclusion followed logically from established premises. The opening sections described the basic prism experiments in careful detail, providing precise instructions for recreating my observations. I wanted every reader to witness personally the separation of white light into colors, to see with their own eyes the phenomenon that had first revealed light's true nature. No amount of theoretical argument could match the persuasive power of direct experience. I then proceeded to the mathematical analysis, showing how each color's behavior could be described by precise laws relating to refraction and reflection. The quantitative relationships I had discovered provided objective standards against which any criticism could be tested. Critics might dispute my interpretations, but they could not argue with mathematical measurements that any competent investigator could verify. The middle sections of optics extended the basic discoveries to explain a wide range of optical phenomena. The colors of soap bubbles, the rainbow, the blue of the sky, the changing hues of heated metals all could be understood through the principles I had established. What had seemed like disconnected curiosities revealed themselves as manifestations of the same underlying mechanisms. I devoted considerable attention to the practical applications of optical theory, describing improved telescope designs, methods for grinding lenses and mirrors, and techniques for controlling chromatic aberration. These applications demonstrated that my discoveries had value beyond mere philosophical interest. They could improve human ability to observe and understand the natural world. The most challenging sections dealt with the fundamental nature of light itself. Was light composed of particles or waves? Did it consist of material substances traveling through space, or did it represent vibrations in some subtle medium? My experiments revealed light's behavior, but not its ultimate constitution. I presented the evidence carefully, acknowledging the limitations of experimental observation while avoiding speculations that could not be tested. When optics appeared in 1704, its reception differed markedly from the hostile response that had greeted my first paper 30 years earlier. The natural philosophy community had matured, becoming more accepting of experimental evidence and mathematical analysis. Moreover, many of the older generation who had been most committed to Aristotelian principles had passed away, replaced by younger scholars more willing to embrace new ideas. The book's influence spread rapidly through Europe. University professors began incorporating my optical theories into their lectures. Instrument makers used my mathematical relationships to design improved telescopes and microscopes. Artists studied my analysis of color to better understand the effects they created with pigments and dyes. More significantly, optics established experimental natural philosophy as the proper method for investigating nature's secrets. Unlike my Principia, which had relied heavily on mathematical deduction, this work showed how careful observation could reveal truths that pure reasoning could never discover. The book became a model for how natural philosophers should proceed, from controlled experiments through precise measurement to quantitative law. Some resistance remained, particularly among those who had built their reputations on theories incompatible with my discoveries. A few continued to argue that colors were modifications of white light rather than its constituents. Others claimed that my experimental results applied only to artificial laboratory conditions and had no bearing on natural phenomena. But these objections carried less weight than they had decades earlier. The mathematical precision of my predictions, the success of optical instruments based on my principles, and the widespread replication of my experiments by investigators throughout Europe had created an overwhelming body of supporting evidence.
Natural philosophy was becoming less about defending philosophical systems and more about testing theories against experimental reality.
The success of optics validated my decision to delay publication until the time was right. Had I published the complete work immediately after my initial discoveries, it would likely have been dismissed as the speculations of a presumptuous young man. By waiting until the evidence was overwhelming and the intellectual climate more favorable, I ensured that the ideas would receive the careful consideration they deserved. The book also demonstrated the power of systematic investigation over isolated observations. My early prism experiments, while striking, had been vulnerable to criticism precisely because they stood alone. By embedding those experiments within a comprehensive framework of mathematical relationships and practical applications, I transformed them from curious anomalies into foundational discoveries that revealed fundamental truths about nature. As I watched optics gain acceptance throughout the learned world, I reflected on how profoundly our understanding of light and color had changed since my student days at Cambridge. What had once seemed simple and obvious, the pure whiteness of sunlight, the fundamental nature of individual colors, had revealed itself to be wonderfully complex and mathematically precise. The transformation extended beyond mere technical knowledge to influence how natural philosophers approached their work. The success of experimental optics encouraged similar investigations in other areas. Heat, electricity, magnetism, chemistry all began to be studied with the same combination of controlled observation and mathematical analysis that had proven so effective in understanding light. I had lived to see my youthful discoveries become accepted doctrine, my controversial theories transform into standard teaching. The prism experiment that had once seemed to overturn the wisdom of ages now appeared in textbooks as elementary demonstration of light's composite nature. What had required courage to propose now required no courage to accept. Yet I remained aware that future discoveries might overturn or refine even these well-established conclusions. Natural philosophy advanced through the continuous testing of ideas against experience, not through the preservation of any particular system of thought. The experimental method I had helped establish would continue revealing nature's secrets long after my own investigations had ended. The publication of Optics marked the completion of my life's work in natural philosophy, the culmination of investigations that had begun with a young man's curiosity about colored fringes in telescope images. From that simple beginning had emerged a comprehensive understanding of light, color, and vision that would guide human understanding for generations to come. As I write these reflections in my later years, more than 4 decades have passed since that first afternoon when I placed a simple prism in a beam of sunlight and watched the familiar world of white light dissolve into a spectrum of colors. The young man who made that discovery could not have imagined how profoundly it would change our understanding of nature, nor how the methods it demonstrated would transform natural philosophy itself. The immediate consequences of my optical work extended far beyond questions of light and color. The experimental approach I had developed careful control of conditions, precise measurement of effects, mathematical analysis of relationships became the standard method for investigating natural phenomena. Students at Cambridge and Oxford now learn to test theories against observation rather than simply accepting ancient authorities. The Royal Society evaluated new ideas based on experimental evidence rather than philosophical argument. This transformation in method proved as important as any particular discovery. Natural philosophy had become a cooperative enterprise, with investigators throughout Europe repeating each other's experiments, extending each other's observations, building collectively toward more complete understanding. The controversies that had once raged over fundamental principles now focused on interpretation of shared evidence rather than defense of competing systems. My work on light had also revealed the mathematical structure underlying natural phenomena, the precise relationships governing refraction, the quantitative laws describing color behavior, the geometric principles determining optical effects all demonstrated that nature operated according to mathematical rules as exact as those governing geometry or arithmetic. This recognition encouraged similar mathematical approaches in other areas of natural philosophy, leading to quantitative theories of heat, electricity, and chemical combination. The practical applications continued to multiply long after I'd completed my investigations. Telescope makers used my understanding of chromatic aberration to design improved instruments that revealed previously invisible details in celestial objects. Microscope builders applied similar principles to create lenses that magnified earthly specimens with unprecedented clarity. Even artists and craftsmen found value in understanding how colors combined and interacted according to mathematical laws. Yet perhaps the most significant legacy of my optical work lay in what it revealed about the relationship between appearance and reality. The familiar world of everyday experience, white sunlight, colored objects, clear glass concealed mechanisms of extraordinary complexity and beauty. What seemed simple proved composite, what appeared obvious required careful investigation to understand properly. This lesson extended far beyond optics. If light, the most familiar phenomenon in nature, could harbor such secrets, what other discoveries awaited those bold enough to look carefully at the seemingly mundane? My investigations had demonstrated that patient observation and mathematical analysis could reveal truths that centuries of philosophical speculation had missed. The success of experimental natural philosophy also changed how we understood human knowledge itself. Rather than seeking truth through pure reason or accepting it from ancient authorities, we learned to question nature directly through controlled experiments. This approach proved more reliable than either logic or tradition, for nature could not lie or deceive as human reasoning might. I often reflected on how different my life might have been if the plague had not closed Cambridge and forced me to Woolsthorpe during those crucial months of 1665 and 1666. Without that period of solitary investigation, free from the constraints of formal study, I might never have questioned the accepted understanding of light's nature. The accident of historical circumstance had created the conditions for discovery, but I came to understand that preparation had been as important as opportunity. My years of grinding lenses and struggling with telescope construction had given me the practical knowledge needed to design effective experiments. My mathematical training provided the tools for analyzing quantitative relationships. My reading in natural philosophy had shown me which questions were worth pursuing and which methods had proven successful in other investigations. The controversies that followed my early publications, while frustrating at the time, had also served valuable purposes. Critics like Robert Hooke had forced me to strengthen weak arguments, address overlooked questions, and develop more convincing demonstrations. The need to communicate my ideas to skeptical audiences had improved my understanding of the discoveries themselves. As experimental natural philosophy matured and gained acceptance, I watched new generations of investigators extend my work in directions I had never imagined. Some studied the polarization of light, revealing additional complexities in its behavior. Others investigated the relationship between light and heat, discovering connections that suggested deeper unities in nature's operations. Still others explored the physiological mechanisms of vision, showing how the eye and brain processed the information that light carried. These developments confirmed my conviction that natural philosophy would continue advancing through the accumulation of experimental knowledge. Each generation would build upon the discoveries of its predecessors, testing established theories against new evidence, extending successful methods to fresh problems, gradually constructing a more complete understanding of creation's mechanisms. Yet, I remained humble before the vastness of what remained unknown. My investigations had revealed the composite nature of white light, but they had not explained why different colors behaved as they did or what fundamental properties determined their specific characteristics. I had mapped light's behavior with mathematical precision, but I had not discovered its ultimate nature or constitution. These limitations reminded me that natural philosophy was an ongoing enterprise rather than a completed system. Future investigators would need to probe deeper, ask different questions, develop new experimental methods. The techniques that had served my generation might prove inadequate for the challenges that awaited our successors. Nevertheless, I felt confident that the experimental approach would continue proving its worth. Whatever light's ultimate nature might prove to be, it would be discovered through careful observation and mathematical analysis rather than through philosophical speculation. Methods that had revealed light's composite character would eventually unveil its deeper secrets as well. Looking back across the decades, I could trace the thread connecting my earliest curiosity about telescope aberrations to the comprehensive understanding embodied in optics. Each step had built upon previous work, each discovery had opened new questions for investigation. The process had required not sudden inspiration, but patient accumulation of evidence, gradual refinement of understanding, persistent testing of ideas against experience. This pattern, I suspected, characterized all significant advances in natural philosophy. Revolutionary discoveries rarely emerged from isolated insights, but from systematic investigation that slowly revealed the inadequacy of accepted explanations and pointed toward better alternatives. The apparent suddenness of breakthrough moments concealed years or decades of preparatory work that made new understanding possible. As I considered what advice to offer future natural philosophers, I thought first of the importance of questioning familiar assumptions. The greatest discoveries often lay hidden in phenomena so common that no one thought to examine them carefully. White light had been familiar to every human being who had ever lived, yet its true nature remained unknown, until systematic investigation revealed the complexity concealed within apparent simplicity. I would also emphasize the value of precise measurement and mathematical analysis. Qualitative observations, however striking, remained vulnerable to alternative interpretations. Only quantitative relationships provided objective standards that could settle disputes and guide further investigation. The future of natural philosophy lay in extending mathematical methods to phenomena that had previously been studied only descriptively. Most importantly, I would counsel patience and persistence in the face of criticism and setback. Revolutionary ideas inevitably provoked resistance from those committed to established doctrines. The path from discovery to acceptance was rarely smooth or swift, but truth had a power that error lacked, and careful investigators who persevered in presenting evidence would eventually see their discoveries acknowledged and embraced. The prism that had first revealed light's secrets now rested quietly in my study, a simple piece of glass that had helped transform human understanding of nature itself. That transformation would continue long after my own investigations had ended, carried forward by new generations of natural philosophers armed with the experimental methods and mathematical tools that my work had helped establish.